So good afternoon, everyone. Thank you very much for joining us today on this Lunch and Learn opportunity. It's my great pleasure to welcome all of you and introduce Dr. Robert Hargraves. And not only because he's my father-in-law, but because he's got a very, very compelling case and presentation to share with us today on safe, sustainable, economical energy from thorium. And obviously, as Schneider employees, we focus on being the global specialist in energy management. So that's very relevant to us professionally, but also in our personal lives. We'll be touching on various front page issues on the environment, climate change, air quality, etc. that affect all of us. So for background, Dr. Hargraves went to Dartmouth College undergrad. He got his PhD in physics from Brown University, and he's got decades of experience. Starting as a math teacher, and then being a software entrepreneur, as well as a technology consultant with Arthur D. Little, and finishing his corporate career with Boston Scientific as a chief information officer. And it's really hard to call him retired because I barely can keep track of all the things that he does, traveling extensively and publishing a number of articles and books, one on thorium that he came out with a couple of years ago, and then a number of articles in American Scientists and other publications. He's also given talks on the topic throughout the U.S., in the U.K., and he's gone to China as well, and he was just invited to Taiwan to present his information as well. And he's had a chance to present at a Google Tech Talk on the West Coast, as well as in Cambridge recently. And we have a Google person who liked the presentation so much that he came back to see it again. So looking forward to the presentation. And by the way, his New Hampshire car license says thorium. So if you're looking for him in the parking lot later, he's right there. Thank you very much, and looking forward to the talk. Go ahead. Over to you, Bob.
Thank you, Christophe. This picture kind of starts off with one of the world's problems, and it shows several of them in just one picture, particularly in the developing world. This is India. And when you look at that picture, you notice a couple of things. One is the economy isn't doing very well because people are employed gathering wood. Second thing to notice is that they're using that wood for energy. Energy is created in India by burning wood and dung, and leads to many health and pollution problems. Another thing to notice is that burning wood and clearing the land is not that good for the environment. And last but not least, these are all women. These women are rather poorly employed full-time collecting wood. So they don't have time for other activities that would allow them to have education and perhaps get a better job in the labor force. So that's one of the problems we hope we can solve. But first, let's do a little bit of economics from a guy who didn't do very well in economics. But look at this chart of government debt versus GDP. It's not just the U.S. that has a problem with its debt crisis. Many other countries are teetering on the edge of having the amount of debt they owe greater than the whole productivity of the economy for a whole year. So how can we solve that problem? Well, there are risks to the problem. We have examples of these risks are right here. And we have solutions to the problem that are proposed by Democrats and Republicans. At the top, many people say we can solve the debt crisis by cutting back on spending. Others say, well, we need to spend more, expend our way out of this problem. How do we solve that? Yet another group says, well, why don't we devalue the dollar in order to increase exports? That'll increase jobs and productivity in the U.S. and get us out of this crisis. But of course, if every country does that, no one will succeed. There's yet another solution, though, and that is to increase productivity. if we can increase the productivity of the economy, we can increase things like tax revenues, government services, and so on, and also reduce the debt. One example of a pulse of improved economic activity had to do with the Y2K crisis in the year 2000. We had many computer software programs that had year numbers that were 2 digits long. And there was great concern that things like controllers for power plants and so on would fail when the year changed from 00 to 01. And that software was embedded into so many systems that so many CEOs were frightened that they said, well, if we're going to fix this problem, let's fix it by putting in a whole new software system. And the concept of enterprise-wide software was adopted by many large firms, with software from Oracle and from SAP and so on. It turned out that that pulse of improved software to handle the entire business spectrum, from HR to accounts payable to receivables to bills of material to manufacturing control and so on, was a boost to the economy. It gave a little bit of a pulse to GDP. Can we do the same thing with energy? Cheap energy. Problems you all know about: global warming, the iconic polar bear, the population of the world growing from 7 to perhaps 9 billion, the loss of the large fish in the sea that we used to eat a lot of, and the wars over natural resources. This is an example of tanks in Kuwait retreating behind oil wells that were set afire by the Iraqis after the invasion to try to capture the oil resource that was there. Coal emissions alone cause many deaths worldwide, hundreds of thousands, particularly in China, because their coal plants emit particulate emissions. But coal is the largest source of energy in the world today, electrical energy anyhow. Global warming is an issue for many people. In my opinion, the biggest problem is the effect on growing food. In this example of a glacier, over a period of time, the glacier began to melt, and so it doesn't have now the ability to stream fresh water during the summer and store snow and ice and so on during the winter. To the extent that happens and we lower our agricultural productivity, we may have starvation problems in countries like India. Yet another is to look at the importance of a prosperous population. Here's a chart that shows one dot for each of dozens of countries that I got from the CIA World Fact Book. And it shows for each country the numbers of children per woman, and it also shows on the vertical axis the GDP per capita in that country, GDP being very closely related to income per capita. And the stable replacement rate is about 2.3 children per woman. And you can see just by examining that picture that it's the poor countries, the poorest, that have the most children and are responsible, in a sense, for the overpopulation of the planet that seems to be facing us. I picked a number. I said about $7,500 per person per year is about the rate that seems to distinguish those countries that have a stable birth rate from those that do not. All those countries to the left of the line, like the US, have diminishing birth rates. Places like Italy have something like 1 child per couple. Most of the population growth in these nations is due to immigration. Now, prosperity depends strongly on energy. You can see from the same chart. Prosperity versus, in this case, electric energy, kilowatt hours per capita per year. Electricity is an important energy source because it can be used not for many things. It can be used for refrigeration, water purification, sanitation, transportation, cooking, commerce, industry, transportation. has many, many uses, and it's the key to a developed civilization. And you can also see that somewhere around $7,500 a year is achieved with a generation of about, again, 2,000 kilowatt hours per person. That's an average of about, I think, 70 or so watts per person of power. In the US, our consumption is much higher than that. It's about 12,000 kilowatt hours per person, off the chart. Some countries are even higher, but countries like China, which are emerging and have a stable population and are emerging, have a prosperous growth, are around that 2,000 kilowatt hour level. But there's another idea too, and that is that prosperity depends not just on energy, but it depends on cheap energy. Here's a chart from, I think, Business Week or the Wall Street Journal that shows the price of oil in red, and you'll notice that when it spikes, it tends to create a recession. Well, we can't argue that it's directly causative, but it's very suggestive that recessions are triggered by excess energy prices. A lot of people have done modeling of economies, and in their belief, they see that energy is not like a normal commodity. It's a kind of thing that's important to everything that happens in the economy. And so a pulse of energy of about $1 worth injected into an economy for about free results in $5 to $7 of increased GDP growth. And that's the reason I'm suggesting that we can use that kind of prosperity pulse to perhaps get us out of our debt crisis. Now, many nations know how key energy is to their own prosperity. And so here you see, particularly in Asia, that people are going to burn a lot more coal in order to get enough electricity to have their people enjoy some of the benefits that we enjoy here in the US and in the rest of the OECD nations. Yet here in the US, we are very concerned with global warming and CO2 emissions, and we are asking much of the world to reduce their CO2 emissions. Here is a chart from a China newspaper a couple of years ago, and they like to point out that the West grew its economy by burning coal and putting that CO2, 400 parts per million, into the atmosphere. And they say the US gained that advantage, Europe gained that advantage, we want the same advantage. We will talk about reducing CO2 emissions when we're at parity with those emitted by the rest of you. And you can see at the bottom the tremendous difference per capita. Now, other people say, well, we ought to have treaties to perhaps make sure that we all commit to this. But if you ever watch Fareed Zakaria, who I kind of like, he wrote this book called The Post-American World 2.0. And one of the points in that book is that the economies of the world are now so intertwined with transportation that it's the dominant relationship between countries. It's not treaties that we put together. And so economics is going to be more important. We need an economics-based solution to this problem. And we can see that political attempts don't work. This is the result of the United Nations IPCC series of conferences that started with Kyoto, right? They've achieved nothing, time after time, and we still keep going back. The latest one in Durban had 13,000 registered attendees trying to solve a world problem. It doesn't happen through political negotiation. People say, well, we ought to conserve. We ought to have less energy consumed in the U.S. So I take the example of electric power in the U.S. Average electric power about 434 gigawatts. That's 434,000 megawatts being generated constantly. A gigawatt is about the power generated by one large electric power plant. So if we cut that in half, what would happen? Well, let's assume that the rest of the world wants the same kind of lifestyle as we would have with half that amount of electricity. You can see that it's going to go up because of Indonesia and China and India and so on, that all need electric power desperately. So we really need, if we believe that economics is the way to get to the solution, energy cheaper than coal. So, how much does energy cost? How much does coal electricity cost? We're going to go through 4 or 5 little models about the cost of energy. If you want to build a new modern coal plant, it costs about $2.8 for each watt of generation capacity. So a big gigawatt coal plant would cost about $2.8 billion to build. Now, that capital cost has got to get recovered in the cost of the electric power that's generated. And we use the concept of present value to understand how that works. The concept of present value answers the question, which would you rather have, $1,000 now or a penny an hour for the next 40 years? Well, the answer to that question depends upon the interest rate you presume, and it also depends upon how many of those hours, in how many of those hours you will actually collect the penny. So if you do that, it turns out $1 invested in a plant at 90% online activity, with an 8% cost of capital, is about a penny. So that's a simple model. We're going to use that forever. Now, if we do that and we look at the cost of coal in the US today and figure out how many BTUs there are in a ton of coal and how much power that will generate and so on, that says the cost of the fuel is about 1.8 cents per kilowatt hour generated. Remember, at home you pay about 15 cents a kilowatt hour for the electricity you receive from the power company. They buy it from a coal plant or someone else, in this case a coal plant, for about 5 or 6 cents a kilowatt hour. In this model, I've kept it simple so that the model doesn't change as we look at different fuels. I've said that the operations cost, to maintain the generators and so on, is about a penny a kilowatt hour. The fuel is going to vary depending upon the source. Now, the pretty picture at the lower left is in Florida. It's the country's only integrated gasification combined cycle power plant. Why is that important? That's the kind of power plant that people want to build in order to do carbon capture. If you want to capture the CO2 from a coal plant, you have to get it out of the flue gas. And the flue gas today contains a lot of nitrogen and nitric oxides. So if you burn the coal in an oxygen atmosphere, the way these plants do, then the flue gas is essentially CO2 and H2O, and you can get the CO2 out. But just creating a plant like that is at least as expensive as that slide indicates today, and that excludes any carbon capture. Let's go do the same exercise again with this famous natural gas. The capital cost of a natural gas plant is pretty low, about $1 a watt of capacity. It's pretty good, really. Fuel is a little more expensive than coal at 2.8, but altogether we're looking around 4.8 cents per kilowatt hour. And in my case, I modeled it with gas costing $5 per million BTU, which is the sort of the market denominator for natural gas power energy. The nice thing about the natural gas combined cycle power plant is it's very clever in the sense that it burns the natural gas just like in a jet engine, but then it takes the heat of the output of that natural gas plant and it boils water and runs a steam generator, and it makes it highly efficient, 60%, which is one of the reasons it has a relatively low cost of energy. Most of the natural gas turbines in the US today are the so-called combustion turbines. They don't have that other part of the turbine that boils the water that creates the steam. The reason that's important is it's less efficient. It also has an impact on wind power because a natural gas combustion turbine can come up to speed in a few minutes when the wind stops blowing, whereas a more efficient combined cycle natural gas plant takes almost an hour to get up to speed to actually replace that electric loss. So wind tends to couple with the combustion turbines, not the combined cycle plants. The other point I'm going to make is that this natural gas boom isn't going to last forever. There's the price of natural gas in Louisiana of a year ago, and there's the price in Japan today, and we liquefy and import it, and there's a lot of activity going on in the Louisiana area to build liquefaction plants at a cost of billions of dollars in order to drain more natural gas out of the U.S. and ship it overseas for a substantial profit. The other point to notice is that oil is a lot more expensive than natural gas in terms of the energy that's being delivered. So for example, you'll hear Boone Pickens talking about we should change our truck fleet in the U.S. to run on natural gas rather than gasoline. Even the EIA projects that the prices are going to go up. There's the historical price. It's been very spiky in the past few years, but the new fracking technology has improved the availability quite a bit. Wind. Everyone loves wind power. Let's do the same analysis. I was very generous. I said 40-year lifetime for the wind, just to make sure that that doesn't affect the modeling. And how much does it cost for a watt of wind power generation capacity? The EIA, the Energy Information Administration of the U.S. Department of Energy, is usually pretty good. They estimate $2.44. I think that's kind of low, frankly. And so what I do is, in this modeling exercise, and I would encourage you to do the same, go out and try and find out what the plant costs. It's very hard to find out because the figures in the newspapers are usually somewhat hidden. They say, well, the government's guarantee this much, or there's a subsidy of this much, and so on. It's hard to know what it is, less all the subsidies. But try and find those things out. Deep water wind off the coast of Rhode Island, $7 per watt capacity. Cape wind, $5.80 right here off the coast of Cape Cod, if they build it. But the other important point here is that you can only recover your money when the wind is blowing. So the capital cost, when distributed over the number of kilowatt hours, increases. So in this case, the capital cost in order to recover just the investment is 17.4 cents per kilowatt hour. The fuel is free, so we're looking at about 18 cents a kilowatt hour. People say, oh, it shouldn't cost that much. But in fact, if you look at the contracts that have been signed between Cape Wind and the utilities in Massachusetts, they start at 16 cents a kilowatt hour with escalation charges up to 24 cents. So if Cape Wind is bought, the utility companies are required by the state law to purchase that electricity at those prices instead of the prices they pay today, which are on the order of 5 or 6 cents. Solar electricity, same sort of story here. I found, and again, if you look hard, you can find the costs for these power plants. The one in the Bright Source plant in California, $5.60 a watt. Another one in Arizona, that price. The capacity factor around here, at least, is much less, around 20%. You might do 25 or 30% in Arizona, actually. But let's, again, look at the model. Is the model right? Here's the prices that were agreed to between the utility companies and the providers. Albiasa in Arizona made a deal for 35 cents a kilowatt hour. Utility companies are required to buy that power whenever it's available, spread it into the rate base, and charge all the customers for it. In Vermont, All Earth gets 30 cents an hour for the electricity it generates. That's on top of the fact that All Earth, when it did its capital campaign, got 30% of the capital contributed by a tax rebate from the federal government, and another 30% of its capital contributed by a rebate from the state of Vermont. So even so, 30 cents an hour is the price. Biomass. Well, I was looking at ethanol, all that sort of thing. I said, well, the cheapest biomass is going to be just taking wood and burning it, never mind processing it in a chemical plant. Let's burn it. So I took my class on a tour of all kinds of power plants. We went to the one in New Hampshire. Here's the deal there. Capital cost examples. I settled on $4 a watt as an example. So it's going to cost 4 cents a kilowatt hour just to recover the capital, almost 5 cents for the fuel, and so on. Here are examples. I called around and found out what people were selling wood to the power plants and convert the wood to BTUs, to kilowatts of power, and so on. And that's how we came up with that number, not almost 10 cents. So green energy is not cheaper than coal. Almost no one says that. Subsidized green energy might be, but what we need to know for the world is what is the true cost. It's not important who pays, whether it's the ratepayer or the bondholder or the taxpayer. What's important to the society as a whole is that we're doing the right thing to improve the GDP. And so, in the long run, people are going to adopt the least expensive source, particularly the developing countries, because they can't afford it. They don't have any money. They desperately need that power. So here we are. Coal, 5.6 cents. And for now, natural gas, underselling it a bit. And these others are somewhat expensive. And here's a plot of what's called carbon intensity. That is the CO2 emissions per unit of energy generated for the world over many, many years. And you see it's flatline. Nothing's happening. So I say it doesn't work. Can nuclear do the job? Well, let's talk about nuclear power for a minute. Alvin Weinberg was a co-inventor of a nuclear power reactor called the light water reactor or pressurized water reactor, and he proposed it to Hyman Rickover's team, who was to build a nuclear powered submarine. Understand, at that point, there had never been built a nuclear power plant anywhere, and the only thing they had was an atomic bomb. So this was a great undertaking that Rickover led, using the design, and that's a figure from a U.S. patent that wasn't published until many years later, that Weinberg's signature is on. And Rickover was a driven person and a strong personality. He, in that picture, has a civilian suit on going into a submarine. You know, he was one of these guys like Lawrence of Arabia that didn't give a damn for the uniforms. He went in the sub on his civilian clothes. He was also the director of the civilian part of the program in the U.S. as appointed by President Eisenhower. And he took a design for a nuclear power plant and adapted it, and had it become the Shippingport, Pennsylvania power reactor, the first commercial electric power production reactor in the United States. He had two companies, GE and Westinghouse, working on nuclear power plants. He had people graduating, so to speak, from submarine school who were trained as operators. So he was also staffing those power plants. And that momentum led to the domination of the United States nuclear power industry with light water reactors. Can they compete? Here's one in Wisconsin that just shut down. For some reason, they seem not to be able to lower their operating costs to compete with natural gas at 4 cents or so a kilowatt hour. I'm still surprised at that. Vermont Yankee has a similar situation. They're shutting down at the end of this year, and they claim it's for economic reasons. So, the question is, why are those reactors so expensive? And I say it might have something to do with the fact that they're based on solid fuels. You've all seen these pictures of nuclear power plant fuel pellets in long cylinders of zirconium that are in bundles that go into the water and inside the reactor. There's a new one coming. The Westinghouse is the latest and greatest, first in decades that's being produced in the U.S. There are 4 nearing completion in China right now. There are 4 under construction in the U.S., in Georgia and the Carolinas. And I just do the math again. If it costs $16 billion for that much power, you know they got to do capital and cost recovery of 6 cents a kilowatt hour. So the cost of fuel is going to be at least 8 cents, could be more. That's a little expensive compared to coal. So it's not cheaper than coal. Worldwide, maybe we could do AP 1000s cheaper worldwide, possibly. That would be good. Then we could compete on a global basis with coal and perhaps solve our problem. But let's look for a minute at some other ways to approach the problem. Let's look at innovation. You probably know Elon Musk, who invented or PayPal and Tesla Motors and SpaceX. Right? All those companies are Elon Musk companies. He looked at the issue and said, we need cost innovation. The situation was old technology. The situation was complex shuttle design. So he says, let's have a new team, low overhead, a new rocket engine, and 6 years after incorporating the company, they had their first rocket flight. Only 6 years. That's really a good number. SpaceX did it for $443 million. The NASA estimates before SpaceX got into the business were those numbers, up to as much as $4 billion. So the innovation was lacking from the NASA approach, and Musk was able to pull that off. Can we do the same thing with liquid fuel nuclear reactors instead of solid fuel nuclear reactors? A little bit of physics just for a minute. Here's what happens inside a nuclear power plant. A uranium atom, a 235 atom of uranium, absorbs a neutron, becomes unstable, and falls apart into two other smaller atoms called fission products. In this example, the krypton and barium. But they could be things like iodine or cesium or xenon or whatever. There's a lot of things that happen, and extra neutrons come off. And you probably know that that's the source of the chain reaction that causes more uranium atoms to fission and so on. And it releases energy. But today's reactors only use some of that. About 3% of the possible energy from uranium is used, and eventually that fuel is taken out of the reactor. One of the reasons it comes out of the reactor is because it's solid. It's uranium oxide. It's in a cross-section. It's been heated to perhaps as high as beyond 1,000 degrees centigrade in the middle. It gets stresses and so on. The fuel pellets are somewhat damaged. They have to be encapsulated in zirconium rods that need to sort of protect them, not only while they're in the reactor, but when they're in storage as we hide or put away or sequester that used fuel. So that's one reason we think that liquid fuel reactors can avoid a bunch of problems. Now, uranium-235 is not the only fissionable material. It's the only natural one. But inside nuclear power plants, we can also make two others, uranium-233 and plutonium-239. This is a chart that looks a little bit like the periodic table, but it's different. The columns correspond to elements, and the numbers, like thorium-90, is the number of protons in that atom, and the rows correspond to the total number of neutrons plus protons. It's the atomic weight of the material. So let's look about what happens there. In a power plant where there are a lot of extra neutrons, actually the uranium-238 absorbs the neutron and becomes uranium-239 that then decays to become plutonium. In a power plant, that plutonium is fissioned. You don't realize it, but all the nuclear power plants around here, near the end of the fuel cycle, have a lot of U-238 converted to plutonium, and a third to maybe a half the energy in that fuel rod is coming from the plutonium. We literally burn plutonium in nuclear power plants. The same idea here, thorium, another heavy metal, also absorbs neutrons and decays and becomes uranium-233, another material that when split releases energy and so on. So we have other sources of fissionable material that we can create in a nuclear power plant. Only the uranium-235 is natural. It's 0.7% of the uranium. So there's not a lot of it, but we can make good use of the thorium as well. Well, Weinberg, the same guy who invented the light water reactor, also invented something called the molten salt reactor. What he did instead was to dissolve thorium fluoride in a salt, a molten salt, not table salt, but in this case, a salt of things like zirconium fluoride or sodium fluoride or beryllium fluoride or so on. So there are various salts that have a low enough melting temperature that they can sort of be the host for a power reactor. The nice thing about that is you don't have all the stresses and things, problems about a solid fuel reactor, and you can handle the fuel, put it in and out much more easily, to say nothing of the lower fabrication costs. He did that reactor, and then he did another one thereafter that ran for many years. His idea was that this was going to save the world because it was an inexhaustible source of energy. And he's right. There's enough thorium in the world that we could run this sort of power for the whole world for millions of years. So that successfully ran at Oak Ridge for years. Now, there's another design that we've been all looking at in some of our work. And in a sense, it makes use of the fact that all of these things can provide energy in a nuclear power plant in that neutron flux that's creating more U-233 and more Pu-239. So this is the so-called denatured molten salt reactor. And the way it works is it's a big vat, a vessel, filled with that molten salt. And there are a lot of nuclear reactions going on in there. You see some examples of the U-233 decaying, setting off a neutron that falls on a U-238 atom that absorbs it and becomes plutonium, and so on. Those kinds of reactions create a lot of heat. And in this kind of a power plant, you get that heat out by going to a heat exchanger, like your car radiator, and transfer that heat eventually to a series of heat exchangers to perhaps steam or helium that runs a turbine that runs a generator that generates electric power. The salts go back into the vat, and you can clean them out a bit on the way. You can take out some of the noble gases like xenon and krypton. You can take out some of the noble metals. And in the future, we can filter out a lot of the other kinds of fission products we mentioned before, like cesium and iodine and so on. A nice advantage of this kind of reactor is it's denatured, which means that it's at least 80% U-238 and at most 20% U-235. The reason for that is that's the IAEA definition of a kind of uranium that is safe in the sense it can't really be made into a nuclear weapon. So it satisfies a lot of the requirements for proliferation resistance. Now, we believe that these sorts of reactors can generate power for 3 to 5 cents max per kilowatt hour compared to the competition. That's what the book is all about, energy cheaper than coal. And there are several outfits working hard to achieve this. Why can it be that cheap? Well, again, the concept is a liquid fuel. And in this case, it's a salt of fluorides. The uranium or thorium or whatever is dissolved in that salt. The salt is good for heat transfer. It has a lot of heat in it. And we can just transfer the heat right out of the reactor in that salt containing those fissile and materials. And the other nice thing about this reactor is it's at atmospheric pressure. So a normal pressurized water reactor is over 100 atmospheres of pressure. So it has to be a lot bigger and stronger. It has to have a lot of extra safety attention to make sure that there's no propulsive force that could somehow push radioactive materials into the environment. In this example, what they did at Oak Ridge was to have what was called a freeze plug at the bottom of the reactor. It was just a little plug of salt that was solid. It was kept cool by a fan blowing on it. And if there was a problem with the fan or something else, and it stopped, that freeze plug would melt, or if the reactor overheated, it would melt, and drain all that liquid out of the vessel into the drain tank, which was configured in such a way that it couldn't be critical and would stop the reaction. So it was a nice design. It didn't rely on any kind of electronic or mechanical system to create the safety. It was a physical principle that was at work here. No propulsive pressure, we mentioned all these. And the other thing is that if we have a rupture, the salt, the liquid salt, will go to the bottom of the reactor room or whatever you have. It will be hot, and it will eventually cool and solidify. It's not going to escape as a gas or something into the environment. The initial design for this thing was to actually power an airplane. We've kind of given up on that for a while, but you can see that the reactor that they had designed was about 1.4 meters in diameter. So it's quite a small reactor. Compare that to the kind of reactor construction techniques that are underway in China now for the AP1000. There's just the lid of the pressure vessel and the containment dome, I think. 780 tons. One of those might be running at the end of this year. There's another technology that's important. The higher the temperature you can achieve in a power plant, the more energy you can get out. If you study thermodynamics, you kind of see that temperature in from the temperature out, right? That we want to keep that as high as possible. We can get higher efficiencies. But if we get higher efficiencies, we can also reduce the amount of water cooling that's needed in these kind of plants. Or, in a lot of cases, we can simply use air cooling because it's high enough temperature. Not quite as efficient. The engineers like water cooling because it's cheaper to build a power plant. But we can do air cooling in those areas where no water is available. A new technology, which I think is wonderful if it ever gets really completed, is something called supercritical CO2 turbines. And in this example, to scale, you see a steam turbine in blue, and at the very bottom of the picture, you see a little red supercritical CO2 turbine. Now, what's supercritical? You know about the phases of matter being a gas, a liquid, and a solid, but there's another phase. If you really compress something hard and bring it to high temperature, you can get to a kind of a compressible liquid called a supercritical state. And they're able to make highly efficient, small, compact power conversion devices that way. That research is going on at Sandia now, and I just wish it would get speeded up because it could help a lot of technologies. Again, basically the cost of thorium is trivial. There's more thorium in an average oil drum of earth than there's enough thorium in an average oil drum of earth to generate 5 times as much energy as an oil drum of oil. And yet there are deposits of thorium minerals that are plentifully available in India and Turkey and Brazil, North Conway, New Hampshire. There's plenty of thorium around. An advantage of building relatively smaller reactors, and I'm an advocate of this, is mass production. And the aircraft industry is my model. Why do we build these reactors on an aircraft-like production line? Boeing builds things that way, and there are a lot of similarities. We have life safety, we have documentation problems, control, computer-aided manufacturing. All those things are applicable to both the airline industry and the nuclear power industry. And if we do that, then historically we see something called the learning curve. And quantifying the learning curve is done by saying, well, every time we double the number of units produced, we reduce the cost of the unit by some ratio called the learning curve. It's typically around 20%. the aircraft industry and other industries. In the computer IT industry, it's been 50%. In the nuclear power industry, the University of Chicago suggested 10%. If we just use the 10% learning curve, we can see that if we built 1,000 of these units, we might be able to cut the cost down to maybe 35% of what we started with. There's a lot of advantages to a well-disciplined set of engineers in factory producing these units. If we go into the business of producing them at a rate of, say, 1 a day, that'd be a $70 billion US industry just for the power plant construction. That's worth sparking up our economy a bit. What if we were to install those things to replace coal power plants? If we did 1 a day, then in about 40 years or so, we could replace all the coal power plants that exist. That's not enough, it turns out. We're planning to build as many new coal power plants in the world as exist today. Not here in the US, it's anathema here, but India, China, and so on have 1,400 gigawatts of new coal plants on the drawing boards. There are other things we can do once we solve that problem. Well, then we have to attack the next biggest source of CO2 emissions, and that is oil. And oil is a great fuel. It's portable, high energy density. We use it for airplanes and cars and so on. But we can produce hydrogen with high temperature nuclear power. And we can actually use that kind of hydrogen directly in cars or other things. So for example, Honda has a model that runs on hydrogen, and so do some other manufacturers today. So we think of hydrogen as being a terribly explosive and dangerous thing, but it can be contained and managed. Better yet, combine that hydrogen with a carbon or nitrogen molecule to make a liquid fuel. So for example, if we combine it with nitrogen, we can make ammonia, which is under slight pressure, a liquid. Methanol is an example of a fuel that can be synthesized. George Olah, Nobel Prize winner, got the Nobel Prize for carbon chemistry, wrote the book called The Methanol Economy, and he's an advocate of replacing gasoline in our fleets with methanol instead. And that's possible. One of the projects that China is doing right now is synthetic methanol using high temperature nuclear power. Dimethyl ether, another, suitable for diesel replacement. Ammonia, people don't think of as a fuel. Here's a car that was touring the shows in Europe, runs on ammonia. It's a converted Toyota, and I couldn't figure out miles per gallon, so we get, here it is, 19 miles per dollar. That's what I figure that costs. So it's an economical kind of a fuel that could be used. People like carbon-based fuels. They're actually more energy dense, and we're used to handling them. And we can do that, but where do we get the carbon? If we keep harvesting coal or oil, we're going to keep adding to the CO2 problem. Where can we get that sweet carbon? Well, we can get it from the atmosphere, possibly. This is a marginally economical way to do it, even with cheap nuclear power, but it's certainly a way to do it. We can capture the CO2 from the air. A lot of that work was again done in San Diego. In Los Alamos. More recently, the Naval Research Laboratories has actually demonstrated schemes for capturing CO2 that's dissolved in seawater. Remember, the CO2 that's in the atmosphere very slowly dissolves in the ocean. So that's one way to get at that CO2. If we get the CO2 out, we can get the carbon, and we need the carbon to make those fuels. They built this unit on a skid. They were sort of kowtowed in the press. They say, well, what's the benefit of that? But the benefit is that they know all about nuclear power. They have them on their aircraft carriers. They are about to generate a program to generate jet fuel at sea from seawater using nuclear power. They can refuel the jet aircraft in place if they can pull off this. And they've demoed it. Here's a demo. They generated some fuel this way with a small radio-controlled airplane. $5 a gallon. That's not bad. We can also use hydrocarbons from crops. A lot of people are looking at taking switchgrass and making ethanol out of it. I would like to use the hydrocarbons not for the energy, but rather for the carbon itself. If we hydrogenate it, we can get about 3 or 4 times the amount of liquid fuel that we do by just processing it for ethanol. In India, for example, cattle dung is a big source of carbon. Cattle dung and wood are major energy sources for cooking and heating in India. It's expensive to collect. And I point out that we have in the Western world sewers that collect and concentrate a lot of that carbon. There are a lot of opportunities here. So, if we were to proceed, what are the benefits? One benefit I'm pushing today is spark the economy. That is, if we can have cheaper energy, then we can spark economic growth. We've heard this number before. $1 of free energy generates about $5 of GDP. Another thing to keep in mind is the safety of nuclear power. The Paul Scherrer Institute in Germany a few years ago did a study of all the accidents in the industries associated with power from coal, from oil, and so on. They counted the fatalities, and they divided them into the numbers of gigawatt years of electricity that was generated. And natural gas is safer. Liquefied petroleum gas transported on those big ships has on occasion caused major problems. So we have a high number of fatalities per year for that. Hydropower, similarly, when a dam breaks, a lot of people die. The nuclear, we've had one large accident. 28 people died in that year of that accident. But the number of fatalities, actual fatalities, is much lower. So it was safe. Success, we need low cost. I keep harping on low cost. If we can keep the costs down, then we can get this technology launched. I, in previous talks, have talked a lot about a lot of the other advantages of this kind of technology, and there are many, potentially, but we can't do them all at once at the beginning and still achieve the lowest cost. So I say, let's defer all these ideas until we really get production up for an inexpensive power source that people begin to accept. But all these things can be done. Again, I believe economics always wins out. Now, China is doing this now to avoid the pollution problem they have there. But the guy on the left is the son of the former president of China. He was the president of the Chinese Academy of Sciences, and he's the guy who he actually read an article I wrote in American Scientist, got his crew out to Oak Ridge, got $350 million to start a project, and that's their goal. Meanwhile, in the last few months, his goal has been upped. They had expected commercial application in about 20 years. Now they upped it by 15 years. This is a slide he used in one of his talks. Okay? So I got his permission to use his slide before and after London and Beijing. He says, that's why I moved from Beijing to Shanghai. So, they're working on it. Are we? Well, these are ventures in the U.S. that I know of and to communicate with. There is an outfit in Florida with a lot of experience in mass production of ships and that kind of technology, working on that project. Here's a guy who got me interested in the very first place in Alabama, who wants to go for the gold. He's the aim high guy. He says, I want to do all these things. I also want to do medical isotopes because the fission products they created are very useful in cancer treatment. Terrestrial energy in Canada. Again, perhaps a customer could be oil sands, steam. In a nuclear power plant, by the way, half of the cost of the power plant is the conversion of the heat into electricity. That is, the turbines and heat exchangers and cooling towers, all that sort of thing. Only half the cost is the nuclear side. So he can perhaps get around that and get his business started. Right here in Massachusetts, in Cambridge, Transatomic Power has a plan for a liquid fuel reactor to consume light water reactor fuel. And out in Washington State, Bill Gates is the sort of money behind the firm headed up by John Gilliland. But Vice President Jeff Lankowski is very interested in alternatives to the TerraPower model, which is a liquid metal cooled solid reactor. They're interested now in liquid cooled reactors such as I am. They have 10 people working on that project. So all these private ventures just in the US are working on this idea. The problem we have is that we really can't do it. From the EPA point of view, as we stand today, there are so many restrictions on nuclear power that it's hard to get beyond the courts to get a license to do anything. Just look at the last number there. The Yucca Mountain limit. See that looks like an exaggeration, right? 9 nines. They say you can't emit more than 0.1 millisieverts with probability 0.89. That's the law. That's not an invention. That's literally the law. The NRC, again, difficult to deal with. It's prescriptive. That is, they have rules about how you have to do things rather than being sort of adaptive, results-oriented. They're sort of process-oriented. And for startup companies, the NRC is right now a big barrier because you need to be able to pay them for every hour that you spend with them. And they charge about $280 an hour for any work that's done to answer any question you have. And we're talking tens of millions of dollars already for NuScale, a startup in Washington or in Oregon. So it's not likely that any of these companies are going to sprout up in the U.S. Just unlikely. Although I know Flibe Energy has the desire to do that. So the answer is we have a good solution. We can solve the energy crisis with economics. We need some kind of government reform to enable private industry to do this. We don't need a big NASA-style project. All we need is people who have actual regulation that will allow them and their entrepreneurial backers to actually pull this off. Thank you very much.
Any question?
Go ahead, please ask questions.
What has been the reception to this in Europe?
What countries are receptive to this?
Yes.
Well, of course, Europe is more anti-nuclear than the U.S. even, but there's a lot of work going on in France at Grenoble. There's a group of people who are studying molten salt reactors and have a design that's progressed quite a ways. But it's sort of a government lab atmosphere. It's not an industry set to build one at this point. Czechoslovakia, or rather the Czech Republic, has a research group that's doing work there. Norway, as you might guess, has a group studying thorium and solid fuel reactors. So that's what's happening that I know of in Europe.
Okay.
Who's behind any resistance to the changing of the regulations in the U.S.? For example, is the nuclear industry in the U.S. For or against the current regulations?
Question is, who's behind keeping the regulations changing, or who's advocating changing them?
Or not changing them?
I find the nuclear industry in the U.S. is sort of deer in the headlights. They're not very active. So, for example, just 2 or 3 days ago, the EPA submitted a new regulation for krypton emissions. The amount of krypton that's emitted is exceptionally small. Hardly any ever in a nuclear power plant, but there might be some if you reprocessed it. But again, krypton 85 it's a noble gas. If you breathe it, you breathe out. It doesn't react chemically. It doesn't stay in you. And so we have some new onerous regulation about to be imposed. So the EPA is always searching for, frankly, for something new to protect the public. We have a big problem there. And one of my activities this year is to try to work and make those kind of problems more apparent. In fact, I'm giving a talk in 2 days at the American Nuclear Society meeting about the issue of our irrational safety limits. If we could convince people that nuclear power is, that radiation is safe within limits, we could get around a lot of the problems. It's not so much the regulations per se, but it's the attitude that's created that does things like make the interveners sue the EPA and compromise on the limit at Yucca Mountain that had 8 nines in the probability of failure. Okay, it's sort of the indirect impact that's the difficult issue.
Do you think there's influence from the oil and gas industry, a negative influence on lobbying?
Does the oil and gas industry influence this? Perhaps, but we don't know. We don't have direct evidence. They're pretty happy. I think they mostly ignore it. But there's some evidence that they do fight it. But replacing oil and gas we're talking 50 years out. It's a long time. Yeah. Okay, thank you. I have, by the way, several copies of the book. I can autograph them for you. And I'm giving, again, a talk in a couple of weeks on this subject. And a lot of my stuff is on the website. I'll leave a little brochure about the radiation issue as well. Thank you.
Thank you.